Welcome to the next episode of Thermodynamics. Today you're going to learn about the second law of thermodynamics. The second law of thermodynamics is based on a quantity called entropy. Entropy, denoted with big S, is a physical quantity which describes possibility that a system spontaneously changes. It can also be defined as a measure for lack of order in a system. Greater lack of order, greater entropy. Entropy of an isolated system naturally goes in the direction of its increasing. Entropy is a function of state, or state function or state quantity, because it is defined for a system with determined state variables, so it depends only on initial and final state of a variable. It is on an equilibrium state of a thermodynamic system. Change of internal energy is also state function. On the contrary, heat and work are process functions. It has quantities which do depend not only on initial and final value, but also on the process. It has transition between two equilibrium states. So they also depend on the way how this transition was made. We cannot measure entropy, but change of entropy can be calculated as change of heat per unit of temperature. So change of entropy delta S is change of heat delta Q over temperature. It is only true for reversible processes. We know most of processes which occur in nature are irreversible. Their entropy in an isolated system constantly increases. For entropy of an irreversible process in an open system, we have to consider total change of entropy, so delta S total, which is equal to sum of change of entropy in a system plus change of entropy in its environment. Where this sum is always greater than or equal to 0, meaning delta S, so entropy always increases or is constant. If there are two entropy systems of entropies S1 and S2, then the total entropy S is their sum. So S is equal to S1 plus S2. Irreversible processes are defined as processes which can occur in only one direction, which is explained by transition from state of less to state of greater probability, where equilibrium state of the system is the one with greatest possibility, which means greatest entropy. When we have explained entropy, a very important quantity for understanding the second law of thermodynamics, we can see it is the quantity which is the first law of thermodynamics missed. So it is defined in the second law of thermodynamics. The second law of thermodynamics states that isolated system spontaneously transits from a more arranged to a less arranged state and gradually goes towards the state of maximum entropy. If it is already in a steady state, or if a process is reversible, it remains constant. The second law of thermodynamics generally describes conditions under which heat can be turned into mechanical work. To do this, an amount of energy has to be taken from outside of the system. A system which converts heat to mechanical work is heat engine, and it is used for conducting thermodynamic cycles, which are sequences of thermodynamic processes. So let's draw a diagram representing such a heat engine, which has three elements. Hot source of temperature Th, cold sink of temperature Tc, and working body W. In this process of heat transfer participates working substance, which is any fluid such as steam, which can be used to transfer heat from hot source to cold sink. So heat is transferred always in this way. So from hot to cold body. A hot source generates heat which heats up a working substance. And the working substance comes into a working body which does the work. So from hot to working body with help of working substance. This work is part of energy gotten from that heat engine, and at the same time the working substance cools down. The remainder of energy is further transported with help of using working substance to cold sink. So working body does some work, transports some energy thermal energy heat to cold sink Tc, where the working substance cools down. During the process, there is a certain amount of heat lost to surrounding environment, and it cannot be used. It is important to point out that total change of internal energy of a gas in a thermodynamic cycle is zero, because internal energy of initial point is the same as internal energy of the final point of the process, so delta U is U final minus U initial is equal to 0. Here we come to thermal efficiency, which is a very important quantity which has to be considered when describing efficiency of a machine. So thermal efficiency, marked with Greek letter eta, which is defined as proportion of work gotten from a heat engine and heat received during one cycle. Work is equal to difference between heat received by gas, which is 1 in the first half of cycle when gas expands, so it does work, and heat released by gas, when gas is compressed, meaning that work is done on the gas by its environment, which is in the other half of the cycle. So work is difference of these two. So Q12 is heat received and Q21 is heat released by gas, where both of these are positive. If we take that Q21 is negative, since it is the heat which is released by the gas, so and the gas loses a part of its energy, then we would have to put here plus instead of minus. But we said that both of these are plus, so so we have here minus. So we now have that for engine efficiency, this one formula, that eta is work done by the system over energy received by that system. This work is as we've written here over this Q12, or we can write it in this form. The same thing. Theoretically speaking, the efficiency can be 100%, so the ideal, the perfect one, in the case when energy released by gas is 0, which means that all energy received by gas is turned into work. However, this has been shown to be impossible to achieve in practice. So the thermodynamic cycle, which will be used by an ideal heat engine if it was constructed, is we can show on a PV graph. Going from point 1 to point 2 in isobaric process, then from point 2 to point 3 isochoric process, from 3 to 4 isobaric process again, isobaric, so here constant pressure, constant volume, and again here have an isochoric process where volume is constant, and it goes in this direction. So we can see it consists of two isobaric processes from 1 to 2 and from 3 to 4, where pressure is constant, two isochoric processes from 2 to 3 and from 4 to 1, where volume is constant, going in clockwise direction on this graph. In conclusion, the second law of thermodynamics states that it is not possible to construct a machine which would in a thermodynamic cycle take heat from lower temperature sink and transfer it to higher temperature sink without outer work done on the system. This impossible machine is called, so machine which would do that, this impossible thing without outer work done, is called perpetual machine or perpetuum mobile of the second kind. That's all for today. Now you can take a short quiz to test what you've learned in this video. You can find the link in the description of the video. Thanks for watching and stay with us.